All right, welcome back. We're recording once again. Let's leave it like that. No, let's not. Let's leave it like that. So, you already had multiple choice Monday. There it is. That was yesterday. So, you already know about free response Friday, right? That's basically the test. But what's today? Sequence mode. Sequences and series. Let's talk about that. Let's see. What is that about? Kindly consider the following sequence. I have to define what a sequence is. Here's a sequence. Let me think. Okay. 1, 2, 4, 8, 16. And it may or may not be finite. I don't know. I haven't decided yet. That's a sequence. What is a sequence? Tell me. If that's a sequence, what's a sequence? That's an example of a sequence. It doesn't always have to double up. It could be a different rule. No, well, there is the notion of a function here. Ordered pairs, yeah. I'm going to say this is a function in n, where n is discrete. This is a discrete function. I'm not plugging in any number I feel like. I'm plugging in 1, 2, 3, 4, 5 into this. Here's my rule. This is my function, but it's a discrete function. I'm not plugging in anything I feel like for n, like we usually do for a continuous variable x. Any real number goes in the domain, like 1.5, negative 12. No. Here I'm plugging in at the smallest 0. Sometimes I start at 1. And then just whole numbers. 1, 2, 3, 4. So what do I plug into n to get 1? 0. And I plug in 1, I get 2. And I plug in 2, and I get 4. And I plug in 3, and I get 8, and so forth, right? Okay, so that's a sequence. Okay, it's just a set of numbers governed by a discrete function. Okay? This is a series. What's the difference? It's based on this function. What's a series? That would be infinity. That's adding them all up, right, exactly. So say I don't go infinitely many. Let's say I just go up to, I don't know, let's say 3. What numbers am I adding up? 1, 2, 4, and 8, right? So that's 10 and 5 is 15. Okay. So that's a finite series, and if I stop at 8, that's a finite sequence. What if I go on forever? What if I have an infinite sequence? What's the sum? Yeah, this one blows up. But some series, even though you're adding up infinitely many numbers, some series converge to a number. Right? So this could be finite or not, and this could exist or not, depending. Even if you're adding infinitely many terms, you may actually get a number, not infinity here. Yeah. That's one way to define E. Yeah, we're going to get to that. Okay, so now I call this the Caliph of Baghdad problem. Okay, you ready? You are a beggar in the street. You know, like, what's this guy? What was that movie? Aladdin. Like Aladdin. Right? So you're Aladdin. You need a job. You go to the Caliph and he said, look, I'll do anything. Give me a job, right? So he's like, well, I don't know. How about I'll give you a drachma a day to clean out the stables? All right, so a drachma a day. I get a drachma today. I get a drachma tomorrow. I get a drachma the next day. Yeah, well, he had to turn to thievery because the Caliph was too cheap. But anyway. So, but we're not there yet. We're at the beginning of the story. So then, what's his frickin' name? Aladdin. Aladdin. No, not a fool. Aladdin. Yeah, what was the monkey's name? It was, really? All right. So anyway, Aladdin's like, this is for the birds. I can't even, buy my favorite food down the street in the bazaar. What am I going to do? So he goes to the Caliph again. He says, look, I need a raise, man. A drachma is nothing. You got billions and billions of drachma. What the heck? Give me 2 drachma tomorrow. Double it every day. A drachma is like a penny, right? It's nothing. So give me a penny today, 2 pennies tomorrow, 4 pennies the next day. It's not a big deal. Okay? How much money do you get in 1 month is my question. Okay? So say a 30-day month, how many drachma do you get, or how many pennies do you get? Are you rich? What? You get a lot. How much? A million pennies? You think that's what it is, total? Add it all up? $320 million, yeah. $1,000? Pennies?
Millions of dollars.
Millions of dollars? Well, let's find out. Let's ask Hal. Come on, Hal, get over here. Let's go into mode and change our mode from function to sequence. All right, now let's put this over here. Close it. Okay. And then go to y equals. And let's put in this sequence. I'm just going to put this sequence in, just see what the numbers look like. Before I add them up, I just want to see what my paychecks are. My first paycheck was 1 drachma. The next day my paycheck was 2 drachma. The next paycheck was 4 drachma, right? So let's just graph this sequence, okay? So I'm going to write 2 to the alpha n. Where's the n's here? Is that an n? Yeah. Yeah, use alpha for the n. Okay, so 2 to the n. Now this is not the series, it's just a sequence. Now notice this says sequence mode. Hal does not know anything about series. We're going to have to trick Hal to add up these numbers for us, okay? But we'll get there. So what does this look like? Well, you see the numbers 1, 2, 4, 8, 16. They get pretty big pretty fast. Let's fix this window. Let's say I do the first 10. Now, what did n start with? How did I get 1? I plugged in 0. Is that right then? N min is 1? No, make it 0. Okay, I'll leave it at that. I'm just going to do the first 10. Now, I usually match my x min, x max to my n min, n max. So I'll put a 0 here. Now, it's going to get pretty big, right? Are we going to have any negative y values? Nah, so let's get rid of the negatives. Put a 0 there. Get a decent window here. And it's going to get pretty big, right? So how big? 1 million? Okay, I'm going to put 1 million in here. Is that 1 million? Yeah. And if I have 1 million, that's more than 1 million? Not really. 10 to the 6, 6 zeros, right? So if I have 1 million for my y max, my y scale will be 100,000, let's say. So you see tick marks, okay? So let's graph. Yeah, I think 1 million might be a bit much. Right, they were only doing the first 10. And we're not adding them up. We're just saying what's each paycheck separately. So 1 million is way too big. Go back to your window. Let's make it smaller. Well, think about it. The biggest value here is 2 to the n when n is 10. Right? I'm going from 0 to 10, which how many terms are there from 0 to 10? 11, right? 1 to 10 is 10, but 0 to 10 is one more. So I'm going to graph 11 terms, and the biggest one is 2 to the 10, which is 1,024. Right? So 1 million is way too big. So I'm going to put in, I don't know, 2,000. How about 2,000? And how about a scale of 100? Now let's see what the graph looks like. And there it goes. Okay, so it's exponential growth, it looks like. That's good for you, right? If your paycheck grows exponentially every day, that's a good thing. Okay, so the most is 1,024. If you trace it, you'll see you get the 1, you get the 2, the 4, the 8, the 16, the 32, the 64, the 128, the 256, the 512, and the 1,024. All right, so that's your first 11 paychecks in drachma. Now, how do you add them up? Well, let me finish this question. What's the biggest paycheck on the 30th day? That's a lot bigger. All right, so I'm going to change my window. Let's get to the 30th day. I'm going to go from 0 to, well, let's make it 31 days. 0 to 30 would be 31 days, right? And so I'm going to change my x max to match. N and x are basically the same deal here. And how big do you think the last paycheck is? $1 billion? Holy Mazola. The Caliph isn't that rich. All right, let's go back to our 1 million. Oh, maybe, who knows? Let's see. Well, apparently it gets really big. They're way off the screen over here. So 1 million is nowhere near enough for your last paycheck. I'm not even adding them up. Okay.
$1 billion.
Whoops, window. How much? $1 billion? You really want $1 billion?
Yeah.
$1 billion drachma. That's a lot of drachma. How many bags do you need for that? All right, that's $1 billion. That's 100 million.
All the other amounts are insignificant.
Right. But my question is, what is the last amount? Well, I think this is the next to last amount. The last one is still a little bit off. But I could probably trace it. Let's see. Trace it. 2, 4, 8, 16, blah, 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 blah. blah, blah,
Oh,
blah, blah,
the
blah.
last one.
We didn't get the last one, but can I get off the screen? Let's see. This is the one before last is 5 times 10 to the 8th. What in hell is that? 500 million. Okay, can I go, whoops, can I go one more? Yeah, it's off the screen, but you can get it. What is it? No, 1 billion something. 1,073,740,000 something.
Well, that's 30th, they just said 31st.
What?
They just said 31st.
That they reverse?
31st day.
Yeah, the 31st day is 30 because I started with 0,
Oh, okay.
right? Say I started with 0. Okay, so the last paycheck is even too big for 1 billion drachma. Now, my next question is, how much money do you have in the bank? How much money do you have in the bank? If you go for 30 days,
He doesn't put his money in the bank.
well, he put it in the bank because he's actually a thief and he doesn't need the money, remember? Okay. Yeah, he doesn't really need the money. This is all a scam. All right, so how much money do you put in the bank or put in his lair with his 40 thieves somewhere? Okay? What is the sum of all those 31 paychecks? Well, that's a hard question to do by hand. So I'm going to ask Hal, wake up, to do it for me. And this is how you do it. You fool Hal into graphing the sum of partial sequences. The sequence of partial sums, right? In other words, this is what I want. Let me go back for a second. What I want is this. Remember that Hal only knows how to do sequences. I'm going to fool Hal into graphing 1, 3, 7, 15, 31. Hal can graph this. What is that? What does it have to do with this? The second term is the sum of the first two. The third term is the sum of the first 3. The fourth term is the sum of the first 4. If I can trick Hal into graphing the sequence of partial sums, that's what it's called. This is the fourth partial sum. This is the fifth partial sum. The sum of the first 5, right? Then the last term is really the sum of all of them, isn't it? All right, so this is the way that Hal does this. You're going to change this line and put right in front. You're going to do this. Alpha u. All right, I can't see this from here. Where's u? Here? Okay, alpha u sub 1, because we're graphing u sub 1, right? Of alpha n minus 1 plus. What does that mean? That means take everything we added up already and add up the next term and graph that. Then the next time it does it, take everything you added up already, get a new term, add it up, graph that. Okay. So that's how you symbolize sigma notation in sequence mode. Okay, so now how big is this? Well, now notice what we're graphing. We're not graphing this anymore. We're graphing this. And I want to know what the last number is. You want to go to a billion now? 10 billion? Well, how far did we go? We had the billion already? Okay. The only thing that's going to change is the max, right? So, all right, 10 billion you want?
Yeah.
1, 2, 3, 4, 5, 6, 7, 8, 9. Give me it. All right, let's graph it. Is that enough? Sequence setup. Oh, what happened there? What happened there? Let's see what happened there. See, Hal doesn't know where to start. That's what this is about. When you do a sequence of partial sums, you have to tell Hal which is the first value, because this is always getting the next value based on the first few sums. It doesn't know what the first one is. What's the first one? No, 1. The first value is 1. So let's tell him that. Otherwise, it doesn't know what to add to get the 3. He can't generate the first one this way. All right, now let's graph it. Well, it starts to grow here, but apparently, well, I guess 10 billion was too much, right? It's not off the screen. So, all right, that's good enough a window to see what's going on. Let's trace it. Ding, ding. Right, let's do it. We got the 1, the 3, the 5, the 7, the 15, the 31, right? This is working. All right, so let's see what's the last one. I got 2,147,048,480,000 something. Okay, make sure your window is the same as mine from 0 to 30. Make sure your y equals the same as mine. U sub n, u1 sub n minus 1 plus 2 to the n and starts at 1. Otherwise you don't get the same numbers, obviously. Okay, so this is not a infinite series. This is a finite series because I can't add up infinitely many powers of 2 and get a number, can I? It gets so big so fast, forget about it. But a finite number of these terms I can add up, and I did. There you go. Okay? All right, any questions on sequence mode or graphing a series, of which is a sequence of partial sum? Let's try that again. This is Zeno's paradox. Do you know Zeno's paradox? Can you give me the rule? A function in n? If you plug in n equals 0, you get 1/2. N equals 1, you get 1/4. Or if you like, you can start with n equals 1, you get 1/2. Anybody? Ethan? Yeah, just 1/2, yeah, that's it. Okay. So these are the terms of the sequence. This is a discrete function. This goes on forever. What's the sum? Now, if I start with n equals what? To get this, n equals what to start? 1, okay. You don't have to start at 0 necessarily. So what if I add up all these terms? What do I get? Now this is Zeno's paradox, okay? Do you ever hear of Zeno's paradox? Okay, here's a visual. This is not going to be on the video, but okay. Okay, I'm walking. Are you ready? I'm back here. Pretend you're an archer. You ever hear of this paradox? You never heard of this paradox. Where have you been? It's like 5,000 years old. Okay, so Zeno said that motion is an illusion that you can never get from point A to point B. It's impossible. Why? Here's his thought experiment. Pretend that you're an archer and you gotta shoot an arrow to a target way over there. Now, I'm the arrow, okay? What does the arrow have to do? Well, the arrow has to get at least halfway there, right? To get to the target. Is that okay? But then from here to there, it's got to get halfway there, right? And from here to there, you got to get halfway there, and halfway there, and halfway there, and halfway there, and halfway there. And you never get there. Ancient Greek mathematics did not understand the concept of limit. In the limit, you get there. That's what that is. What if I add 1/2 of the trip, and 1/4, and an eighth? This is only an eighth of the whole thing, right? And a 16th is only a 16th of the whole trip, right? Do I get the whole trip? Do I get 100%? Do I get one whole trip? Do I get one? My guess is that this is one. Now remember what I said. Even though you're adding up infinitely many numbers, you may not get infinity here. You may get a number here, right? In the Khalif at Baghdad problem, that blew up, right? 1 plus 2 plus 4 plus 8 forever, that blows up, boom. But this does not. This equals 1. Let's show that. All right, so let's graph the sequence, and let's graph the sequence of partial sums on Hal and show that limit exists, and it's 1. This is a limiting process. It's like as, you could think of it this way. Let's say you put some value, I don't know, m here, that's m, and you're taking the limit as m goes to infinity, right? So if m is 1, you get 1/2. Just a sum from 1 to 1, just the first term. If m is 2, you get 1/2 plus 1/4, 3/4, right? If m is 3, you get 1/2 plus 1/4 plus an 8, right? 5/8, and so forth. Okay, so 4, 2, 7/8, sorry, and so forth. Okay, do you get 1 if you add them all up? Let's ask Hal to do that. So Hal, wake up. Come on. Let's go back into y equals, where I am in y equals, okay? I don't want the whole series, I just want the sequence terms first, just to see if I can do that. So I'm going to do 1 divided by 2 to the alpha n. Oh. And I'm just going to clear that. Okay, now what's a good window? Window. Well, I don't know if I need 30 of these, but all right, let's start. Okay, let's do it like before, 0 to 10. Is it 0 though that we start at this time? We started 1, right? What we're plugging in, this is what we're plugging in. So let's make that a 1. If you start at 0, it's a different sequence. What if you plug in 0? What do you get? 1. So it'd be different. It'd be 1 plus everything would be 2, I think. All right. Anyway, so there you go. The x values, that's fine. Well, yeah. Well, no, I'm going to 10. Yeah, I like to see the axis, so I'm going to start at 0 here. Although you don't really need the axis for this. Now, this is way off, right? I mean, the first value is a half, and then it gets smaller and smaller and smaller. So how about a 1? How about a 0.1? And let's see what that graph looks like. So it starts when n is 1, you get 1. Oh, wait, let's trace. Where's trace? When n is 1, you get 1/2, right? When n is 1, you get 1/2. When n is 2, you get a quarter. When n is 3, you get a third. Sorry, we said an eighth, didn't we? An eighth. When n is 4, you get a 16th. That's a 16th, and so forth. All right, so now how do we get the sum of these values? We've got the numbers. What do you do to this? How do you change this line to get the sequence of partial sums? You do alpha u sub 1, since I'm in the u sub 1 line, of alpha n minus 1, close it, plus, what goes here? First term, right, so 1/2 or 0.5 if you like. Okay, now let's graph that. You ready? All right, let's try it. Look, 1/2 plus a quarter plus an eighth plus a 16th plus a, look what's happening is you're adding less and less and less and less. What you're adding eventually becomes insignificant, and we get to a horizontal asymptote. Let's make that asymptote more obvious. I'm thinking it's going to 1, so let's make a y max of 2 to make y equals 1 more obvious. And let's go and add on, I don't know why it's 30, but 30 terms. What the hell? You have an argument with Hal? That's not healthy. Okay, so look, there it is. It's going to a horizontal asymptote. This is a y max of 2, so this looks like 1, doesn't it? Let's confirm it. Let's do a little convergence table. Alpha u sub 1 of 1 should be a half. Of 10, I don't know what it is. Let's ask Hal. Of 100, I don't know what it is. Let's ask Hal. Now, why is it taking so long? Because it's creating 100 terms and then adding them up. Right? That takes a while. Well, now, is that a convergence table? I got fix 4. Do I have fix 4 convergence? No, I got to do it. Show that it doesn't change if I keep on going. All right, let's keep on going. How about 1,000 terms? Infinite cosmic powers. Same movie. Infinite cosmic powers. Itty bitty living space. Right? Remember that movie? Same movie. This is a Latin movie. Anyway, do we have 1.0000? Come on, baby, you can do it. I know you can. Do it. Do it. I got a feeling. Come on. It's going to be a good... It's busy. See? You know, now this is all right, this is a time for ludicrous speed. Where's my... Yeah. There's a ludicrous speed setting here. Where's my ludicrous speed? Ludicrous speed. Where the frick is it? I forget. Emulation. Where the heck am I? This one. No. I want to put it at my dual core speed, not at the emulator speed. Here? Where? How do I see it? Oh, restrict. There it goes. Ta-da! That's ludicrous speed. In other words, it was emulating the TI-89 speed. Yeah, but...
How did you do that? That doesn't even make sense. That's your boss.
Wait, look, what if I put it... Now, see, it's going so fast, the keyboard is too fast. Wait, hang on. What if I do this? That's going to take forever, right? Well, it would have taken a lot more longer than it is taking. But this is a lot still to do. You wish. Anyway, ludicrous speed is too ludicrous. It's gonna blow. Dang it. Give me your left. Hurry! Before it blows! Ah! No, it's still doing it! Ah! It blew up!
Oh, never go. What am I doing wrong?
All right, I'm gonna bring it back. I can bring it back. Hello, where the heck? Bring it back. You can do it.
Oh, you I one.
That's your first value that you're adding up. Yeah.
All right.
All right. So let's see. Did I lose it all? Dang it. Okay. It's alpha u 1 of alpha n minus 1. What? What? I'm in function mode? Dang it. Yes, mode. Sequence mode. All right, so I did that. Okay, so it's alpha u 1 of alpha n minus 1 plus
Oh, n minus 1.
1 divided by 2 to the alpha n. That's why I'm doing it again. Make sure you got it. And the first term is a half. And my window, God knows what it is. Let's go to 100. Why not? Let's start at 0. Let's go to 100.
Yes.
You got it? Let's go to 10. Let's go to from 0 to 2 in 1. Okay. And that's a nice flat horizontal asymptote, isn't it?
Yeah.
Okay, so what's your homework? Find this sum, find this sum, find this sum, find this sum. Infinitely many. From whatever you can plug in first to infinity. What's the smallest value of n you can plug in? 1. Here? 0, because 0 factorial is 1. Oh, God. Can I plug in 1? I'm sorry, can I plug in 0? No, so plug in 1. Can I plug in 0? Yeah, okay, so start at the smallest value you can plug in and go infinitely many terms and see if we get a limit. See if it exists. Okay? So why don't we try one of these? 1 over n squared. Let's see, so where am I? So all I have to do is change this line to 1 over n squared. So instead of 2 to the n, it's n squared. Alpha n squared. What's the smallest value of n you can plug in? 1. So what's the first term? 1 over 1 squared is? Not a half. It's 1. Enter. No, change it to a 1. Now, is my window good? My first value of n I plugged in was 1. Yeah, that's right. And I don't know how big this gets. Let's see if that's any good. Oh, yeah, look at that. That limit exists, too. It looks like a nice horizontal asymptote. Either it blows up like the Caliph of Baghdad problem, or you get a horizontal asymptote. Let's see what that is. Alpha u 1 of 1 is 1, right? Yes. But what if you add up 10 terms? What if you add up 100 terms? I'm not going to do ludicrous speed again, because it just foobars everything. What if I put in 1,000 terms? Well, that's going to take a little while. But as it turns out, this is a famous series. It happens to be pi squared over 6, exactly. This is known as Euler's series. He stayed up all night one night and figured out this is exactly pi squared over 6. In 1782, no calculators, no computers, no nothing. How do you get that? And it's exact. What? Now, did we get an answer? Window? Yeah. I didn't change the window that much. I just went from 1 to 100, 0 to 100. Yeah, it happens to be exactly pi squared over 6. How the heck he got an exact answer like that, nobody knows. He never wrote down his work. Or he did, but it was lost, so, right? He did it geometrically, using rectangles and triangles and things. I don't know, don't ask. But it has been proven that it's pi squared over 6. This number that we're getting is approximating pi squared over 6. And this is a famous result. There's $1 million prize for anyone who can prove that 1 over 2 to the p is prime, no, p is complex, converges in what it converges to. There's $1 million prize for that. You want $1 million? There's $1 million prize that asks, when does this converge? Not just for 2, 3, 4, 5, does it? 6, 7, 8, does it? What if this exponent is a complex number? 1 plus I, 2 plus 3i, 5 minus 6i. Does it still converge? If it does, what does it converge to? There's $1 million prize to prove this, because if you can, as it turns out, this has something to do with a prime number generator, which there isn't one yet. This is called the Riemann zeta function. There's a theorem that says this converges when this number is complex. That there's an answer, it doesn't blow up. And the question is, when does it converge, and what does it converge to? Can you get me a formula? There's $1 million prize for this. Go to claymath.org and look at all the $1 million prizes there are. Okay, I'll leave it at that. Bye-bye.